So now we're about to prove conclusion 2 and then conclusion 3. We want to prove that the function x that we defined, x as a function of y, is continuously differentiable. Now recall when we used the inverse function theorem and we applied it to capital F, it guaranteed, in this point here, 3 star, it guaranteed that the inverse of f restricted to u is continuously differentiable. So we're going to use that fact to prove that x is continuously differentiable. Okay, let's go down and look at the definition of x. X is, okay, so x sends y to the first component of this thing applied to 0, comma y. Let me try to write this as a composition of functions. And we have seen before that the composition of C1 functions is C1. So that should be sufficient. Okay. Okay, so let's start here rewriting the definition of x. So for y and w, x of y is given by first take y and then look at 0, comma y as an element of Rn plus m. So in other words, embed y. So let's follow along a series of mappings. First embed y, then apply f restricted to u inverse to that. F restricted to u inverse of that. Then project and take only the first component of that. That's x of y. Okay, so from here to here, we applied the embedding. So this is the function that I called iota sub 2 that embeds, it goes from Rm to Rn plus m, right? Except, okay, the y's can't just start anywhere in Rm, they have to start in w, right? So really it's iota sub 2 restricted to w. Okay, and we end up in Rn plus m, but actually we end up specifically in v, right? W was defined so that when we do this we end up in v. Then we apply f restricted to u inverse. So what's going on here is applying this map, which takes us from v over to u. Then we apply, so from u we apply, here we're applying the function pi1, right? And we end up in Rn. So that series of maps, that composition of 3 maps, that is x. And I guess this is actually pi1 restricted to u, if I want to call it a map from u to Rn, rather than from Rn plus m to Rn. Okay, so this is a way of looking at x. It's iota 2 composed with this, composed with this. And let me omit the restrictions just to make it look prettier. But really, this should be restricted to u, and this should be restricted to w. But let me just write it like this for aesthetics. So this is a composition of 3 functions. These 2 functions are linear, right? They're linear maps, so they are C1. They are continuously differentiable. The derivative of a linear map is itself everywhere, so its derivative is actually a constant function, so definitely continuous. So these are linear. So C1. And then this one is C1 by 3 star, that point in the inverse function theorem application that we highlighted a moment ago. So x is a composition of C1 functions. Therefore, x is C1. This was I think we did this in a previous lecture. Therefore, x is C1 by, and Let me pause and find the lecture reference. Got it. It's lecture 6, part 1. That's where we prove the composition of C1 functions is C1. Okay, so that's it for proving that x is C1. Next, we will go here and prove number 3, that if you want to know the derivative of f, then it's given by this funny looking formula.